Okay, so my phone tells me it's already 4. Welcome back. Our last speaker for today is Professor Mike Zaletel. He's from UC Berkeley. He received his PhD degrees at Berkeley and do a postdoc at Microsoft Quantum Computing Division. He actually joined Princeton as a faculty before he became a professor at Berkeley. So today we are very honored to be able to invite Professor Zaletel back to here to give a talk. But before we start, I want to know that if you have any question during the talk, please type them in the Q&A box located at the bottom of your Zoom window. Also, don't forget to upvote questions that you think are important. And at the end of the lecture, I will read out a few of them, the most popular one to the speaker. So today, Professor Zaletel will talk about quantum Hall bilayer with a twist, Skyrmion Mediated Superconductivity. So now, Professor Zaletel, it's all your time.
Thanks, Shengli. Thanks for the invitation, and thanks to Ali and the team there. It's too bad I can't be back in Princeton. Also, I'm happy to have interactions during it, so whatever questions you get, I'd love to have them as we're going along. So I was very happy to see the lineup of speakers because we've had a deep introduction to the physics of quantum Hall bilayers. That's going to be a lot of the focus of this talk. So I'm going to give some background on quantum Hall bilayers, like the sort that Professor Eisenstein talked about, but where we add back in the spin degree of freedom, some history there. And the spins lead to these interesting topological textures called Skermions. But in addition to that history, I want to talk on a twist of the quantum Hall bilayer problem, where the presence of these Skermions actually leads to superconductivity. And this new aspect of the story is a collaboration with my postdoc here at Berkeley, Shubhayu Chatterjee, and Matteo Ippoliti at Stanford, as well as collaborators at Harvard, shown below. Okay, so what's the outline? First, I want to talk about history of quantum Hall bilayers, where you put spin back into the problem, and in particular, this analysis of Sachdev and Sharma. And then I'm going to introduce a twist on that model, where I'm going to consider quantum Hall bilayers which are actually time reversal symmetric. And the way I'm going to do that is I am going to consider bilayers where the top and the bottom layer actually see an opposite magnetic field. Now, this might seem like an artificial sort of problem. It'd be very hard to realize literally using magnetic fields. How would you have the opposite bilayers see opposite fields? But it turns out, and I'll touch on this at the end, that the physics of magic angle graphene actually realizes a model quite similar to this. So that was really the motivation for this work. After introducing the model, I'll discuss the numerical way that we're able to handle quantum Hall problems. This is a density matrix normalization group, quantum Hall problem. And then finally, I'll walk you through how you can use DMRG to probe the nature of the superconductivity and show that there's evidence for superconductivity formed from Skermions. Okay, so first some history. We've heard a couple talks actually about excitons, and in particular exciton condensation and quantum Hall bilayers. And in the usual discussion of this, we actually completely forget about the electron spin. So we have two components corresponding to the two layers, but we assume that due to the presence of the Zeeman field from the magnetic field, that one of the spins is basically at higher energy, and so we don't need to worry about it. In terms of what the lambda level spectrum would look like, you basically have two spectra of lambda levels, one in the plus, I'll call that the top layer, one minus from the bottom layer. They're spin split by the Zeeman field, and so you have non-interacting gaps at 0, 2, 4, 6, etc. And then this interesting physics of exciton condensation we heard about occurs when you half fill the spin polarized lambda level. So at nu total is equal to 1. And then you have this interesting physics that there's spontaneous symmetry breaking, and the system spontaneously develops coherence between the two layers, or you can also think of that as a condensate, a Bose superfluid of interlayer excitons. Okay, but really the electrons have spin, and it's quite interesting if we add spin back into the problem. So sometimes this is called a double bilayer. So now I'm going to be interested in the 4 degrees of freedom coming from both layer and spin together. And if I analyze the problem in the limit where the Zeeman energy is considered to be small, physically you could implement this by reducing the G factor, for instance, which can be tuning gallium arsenide by pressure. Then there's an analog of the problem of half filling the spin polarized lambda level, which is to half fill the spin unpolarized lambda level, right? So now, in the absence of the Zeeman field, my non-interacting gaps occur at 0 and 4 because I have 4 copies of the lambda level. And the problem I want to consider is what happens if you half fill that degenerate lambda level. So that puts you at total filling 2. So what's the ground state here? And this is going to be even richer than the problem of exciton condensation because rather than a 2-component space, the various orders which could occur, the symmetry breaking can occur in a 4-component space. So concretely, what's the model we would look at here? It's a simple extension of the quantum Hall bilayer problem. We're going to take lambda levels. There's going to be one term, which is called this symmetric anti-symmetric splitting. That just comes from a possible weak tunneling between the 2 layers. And because I'm going to use gamma to denote layer, this is off diagonal in layer, so it's a gamma z term. That's here. And then second, I'm going to imagine that there's a small but still residual Zeeman splitting, which prefers a particular spin. That's the Zeeman coupling here. And then, of course, I have the all-important Coulomb interactions, which resolve the degeneracy of the lambda level. So this problem has a very rich phase diagram in the plane of the interlayer tunneling. The Zeeman effect, which I believe was first described by Desarma, Sachdev, and Zheng back in 1998. So I want to walk you through what phase diagram they find here. Okay, so we need to fill 2 of the 4 lambda levels. What are the different ways you could do it? Well, it turns out there's going to be 3 competing phases. 2 of them are pretty easy to understand. So first, suppose that the Zeeman energy is fairly large. Then naturally, just at the single particle level, that splits the down lambda levels from the up lambda levels. So to fill 2 of 4 of them, you'll just fill only the up spins, both the top and the bottom layer. So schematically, I'll denote that as you fill layer plus up and layer minus down. And of course, the order parameter for this phase is just it generates a net magnetization in the spin space, but no polarization in the layer space. So that's the ferromagnet. What about the other limit where it's this tunneling between the 2 layers, which is the largest effect? This leads to something that I'm going to call the spin singlet exciton insulator. So it's a little bit hard to draw it in terms of the levels, but we know that the tunneling wants to create a coherence between the 2 layers, right? So it splits it into the bonding and anti-bonding. So when you have large delta, the electrons prefer to go into this positive superposition of the top and bottom layer. And then what you can do is, just because we want to fill 2 and 4, you can always go into a superposition of the top and bottom layer, and then just have the up spins do exactly the same as the down spins. So this phase is really just 2 copies of the exciton insulator we learned about in Jim's talk, where you just take 1 for each of the spin. So in this case, you have coherence between the 2 layers and no net magnetization. In fact, it's a spin singlet. Okay, so we've analyzed these limits where either delta Z is the largest or delta SAS is the large limit. But it's interesting to ask, if you consider the ratio as you tune between these 2 limits, do you go directly from this exciton insulator phase to the ferromagnet? Or might there be an intervening phase sitting between them? And it turns out there is. It's a little bit interesting to see where this comes from. This third competing phase that sits in the middle is actually a layer anti-ferromagnet, and it's called the canted anti-ferromagnet. So here's the picture of it. The way you're going to fill 2 of the 4 lambda levels is you're going to put 1 electron into the top layer, and you're going to choose its spin to predominantly be in the XY plane, say pointing along X. And then the second electron you put in, the second lambda level you fill, is going to be in the opposite layer, and you're going to anti-align the 2 spins. So to draw the picture of that here, plus and minus are my 2 layers, and schematically I can show what's the amount of spin polarization in each of these quantum Hall bilayers or layers. That's the red arrows here. You have them pointing equal and opposite predominantly. And then the canted part comes with the fact that if you do have the Zeeman field on, rather than purely sitting in the XY plane, the 2 spins will tilt slightly into the Z-axis in order to benefit from the Zeeman energy. Okay, so that's the claim. This is actually the intermediate phase. Its order parameter is described by what's an anti-ferromagnet, so it has this nail order parameter. Since gamma Z is plus and minus for the 2 layers, This expectation value here of gamma z combined with spin is just giving the difference in spin polarization between the two layers, so that describes the anti-ferromagnetism. Okay, so what is the physics that actually prefers this intermeeting canted anti-ferromagnetic phase? So it comes from the following effect. Let n be the spin density in each layer. It turns out that you can gain from both the tunneling between the two layers and the Zeeman energy by forming this canted anti-ferromagnet. So how do you gain from the tunneling? Well, most of you are probably familiar with, in the Hubbard model, for instance, there's this phenomenon of super exchange. If you take the spinful Hubbard model, in the strong coupling limit, the virtual hopping between neighboring sites leads to anti-ferromagnetism at order t²/u. So you get this anti-ferromagnetic super exchange. So it turns out there's a very similar phenomenon here. Delta SAS is the tunneling between the two layers. And if it's much weaker than the Coulomb interaction, you can treat it perturbatively. And when you do that, the perturbation theory is almost exactly analogous to how it works in the Hubbard model. And that generates anti-ferromagnetic Heisenberg exchange between the two layers. So the way I'll write that is you get some coupling J, which is like your t²/u times n plus n minus, where that's the spin density in the two layers. Okay, so the canted anti-ferromagnet is happy with that because by definition, you give it almost opposite spin in the two layers. The reason it benefits from the Zeeman is because of the canting effect. If you turn on the Zeeman field and you cant slightly, you benefit from the Zeeman part to first order in the angle, whereas the cost from the super exchange is only second order, right? So what that means is that by canting slightly, you don't penalize the super exchange much, but you directly benefit from the canting. And so this canted anti-ferromagnet gives a nice compromise between the two effects and leads it to be the ground state when you're in the intermediate regime where they're of comparable strength. Okay, so this is this cool physics of canted anti-ferromagnetism. And this physics is actually seen in the quantum Hall ferromagnetism of graphene, actually. I don't have time to get into it here today, but in graphene, you actually have four components, not coming from layer in spin, but coming from valley in spin. But it turns out that the effective model actually looks something quite like this, and experiments have seen that the ground state is indeed this canted anti-ferromagnet. Okay, so in the focus of the rest of the talk, I'm going to take a twist to this quantum Hall bilayer problem, and the claim is it's actually going to lead to superconductivity rather than the exciton condensate. I won't really have too much time to get into it, but the motivation for this is that this small twist on this model is actually an effective description of the physics of magic angle graphene, where instead of Landau levels, you have churn bands. So potentially this could actually be an explanation for superconductivity in that model. Okay, so what's the twist? So the model we discussed so far was a quantum Hall bilayer with a little bit of hopping. And henceforth, I told you that if you treat the hopping perturbatively, it just generates this anti-ferromagnetic super exchange. So going forward, I'm just going to assume we've already done that perturbation theory. I'm going to neglect any hopping between the layers and just directly put the super exchange into the Hamiltonian. So my Hamiltonian then is conventional interacting quantum Hall bilayer with all Coulomb interaction. And then the super exchange, I'll write it in this form here. Remember, gamma z labels layer, sigma is spin. So this just gives the difference in the magnetization between the two layers squared. So this is exactly the preferred anti-ferromagnetism. So that's the model we were discussing thus far. What's the twist? The twist is what I'm going to do is the two layers, rather than having them see the same magnetic field, I'm going to have the top layer see a positive magnetic field and the bottom layer see a negative magnetic field. So all it does is change the single particle term here. You can see that the vector potential, the sign of it now gets locked to which layer you're in. Now, how would you realize this? As I was saying, I wouldn't really know how to do it using magnetic fields and gallium arsenide, but this could be the effective description of any band structure where you have churn bands, where time reversal ensures that some of the bands are churn 1, that's like having a positive magnetic field, and some of the bands are churn -1, that's like having a negative magnetic field. And in fact, a band structure like that does show up in intrusive bilayer graphene, which, as I said, is the motivation for this. But anyways, I'll just consider this continuum model, even though the continuum model itself might be a bit difficult to realize. Okay, so that's the model. And the claim is this Hamiltonian, exactly this Hamiltonian, is actually a superconductor. Anytime you start from this integer quantum Hall ferromagnet at 2 that I talked about and dope it a little bit, when you dope this quantum Hall ferromagnet, you get a superconductor. And this will actually be true for any magnitude of the super exchange. It can be infinitesimally small, despite the fact that you have this long range 1/r Coulomb interaction. So I think this is a pretty surprising result. Okay, so the way I'm going to structure this is first I want to introduce how we're going to numerically solve that model and give you evidence for superconductivity without interpreting it too much. I'm just going to show you how would you tell that there's superconductivity in this model. Once you see that there's superconductivity, I'm going to try and give a theoretical interpretation of it in terms of a very exotic new mechanism for superconductivity, which is superconductivity formed from pairing of Skermions. So let's jump into the numerics. How do we solve this problem? The approach I'm going to use is the infinite density matrix for normalization group. It's an extension of the DMRG algorithm developed by Steve White to the quantum Hall problem. So at the single particle level, recall we'll have a tower of lambda levels split by the cyclotron gap. And let's assume that we're in a large magnetic field. Oh, sorry, I should first say, remember it's a slight twist on the quantum Hall because half the fermions see positively field, half the other. But that doesn't really change the energy spectrum. Whether you have plus B or minus B, you get the same spacing of Landau levels. Okay, so I have this fourfold degeneracy. And then I'm going to go to the limit of a very large magnetic field where the spacing between the Landau levels is larger than the typical interaction between them. Okay, so the typical interaction scale is the so-called E squared over LB, where LB is the magnetic length, because LB is the typical distance between your electrons. Large B guarantees this particular hierarchy there. And so it should become safe to project the full problem. You can take the Coulomb interaction and just project it into the lowest Landau level. Should I answer the question now, Jingli?
Okay, we got one question. Can we just insert anti-ferromagnetic layer to the bilayer and generate opposite magnetic field at different graphene layer and realize the same effect of twist?
Yeah, that would be fine. It's just physically, I'm saying I wouldn't really know if you took literally 2 layers of graphene, how would you apply different B fields to the 2 of them? It doesn't really feel it. I wouldn't know how to do that. You'd need to have like a huge sheet of current between them. So how to realize this literally in experiment, I don't know, but the claim is if you do it with Chern bands rather than Landau levels, then there are models that could realize this physics, and I'll touch on that at the end.
Okay, that's all we have right now.
Yeah. Okay, so the problem now is similar to the way we do standard fractional quantum Hall numerics, going back to even some of the original papers by Laughlin where he did exact diagonalization of this problem. The only complication is rather than diagonalizing the Coulomb interaction in a single Landau level, you now have 4 copies coming from spin and valley, so it's a huge Hilbert space in general. Now, where when you go to diagonalize this problem, solve for the ground state, does the B field change show up? It doesn't show up in the single particle physics at all, right? They're completely degenerate. Where it shows up is that when you look at the single particle wave functions in the quantum Hall effect, you get this famous form where in the lowest Landau level, they look like holomorphic functions. So phi m is a given wave function where z is x plus iy is your 2-dimensional coordinate. And what happens when you flip the sign of the magnetic field is it's time reversal, so it just complex conjugates your wave functions. So the structure of the wave functions looks different in this way. And that shows up when you go to calculate the matrix elements for the Coulomb repulsion. This z to z bar will show up as different interference patterns, different complex numbers on the Coulomb matrix elements, which then changes the spectrum. And it turns out that just that change in the phase is going to lead to superconductivity in this model. So how do we study it numerically? Well, DMRD is a 1D method, right? So you use it to solve for 1D spin chains or 1D fermion chains. This quantum Hall problem is, of course, a 2D problem. So the first step is I need to map 2D to 1D. And the way we're going to do that is start out with a plane and then make one of the directions periodic so that we instead have a cylinder. The numerical difficulty is going to increase with the circumference of the cylinder. In this study, we can study maybe a circumference of 10 or 12 magnetic lengths. So you can kind of think of it as like looking at a lattice model with a circumference of 12 or so. So it's not that thin. Okay, so once we put it on the cylinder, how do we proceed? Well, the way we're going to handle the magnetic field is the so-called Landau gauge, where the vector potential only depends on your distance along the cylinder and not around the cylinder. And when you solve for the quantum Hall problem in the Landau gauge, the wave functions take this really cool form that I've written here. So x goes around the cylinder, as you can see here. Y goes along the cylinder. And the form of the wave functions are plane waves around the cylinder. So they're completely delocalized around. But you can see here there's this Gaussian factor, which causes them to be Gaussian localized along the length of the cylinder. And in fact, if you look at the center of mass of the Gaussian, which is describing, where it's centered, it's locked to whatever the momentum is around the cylinder. So because the momentum comes in discrete eigenvalues, and because the average location of each of these orbitals is locked to the momentum, it maps the problem onto a discrete chain corresponding to each of these Landau gauge orbitals. So, this, of course, is not unique to our study. This approach to putting quantum Hall on a cylinder actually goes back to the early 2000s. I believe Shibata was the first to use the Landau gauge to do this, as well as Berkeley and others thereafter. So to account for the fact that we have both bilayer, we've had both layer and spin, for each particular momentum, you're going to have 4 copies of the orbital that you just sort of interspace into each other, and that leads to a quite complicated Hamiltonian, but in the end, it's a very complicated Hamiltonian, but formally it's still a 1D fermion chain, and then you can just throw it into a DMRG algorithm. We use the 10-pi algorithm that I like to give credit to Roger and Frank Pullman for helping me implement. Okay, so that lets us solve the quantum Hall problem with DMRG. Let me just jump into what phase diagram we end up finding. So to present these phase diagrams, I'm going to make the model slightly richer than the original one I proposed. So again, it's a Coulomb interaction, and these opposite the layers. And then I have this anti-ferromagnetism. I introduce one additional parameter, which is the strength of the anti-ferromagnetism, this Heisenberg coupling. I'm going to allow it to be slightly stronger or weaker in the z direction compared to the xy direction, right? So I'm going to have 3 JIs according to the 3 possible spin orientations. And the xy ones, I'm going to make stronger by a factor of lambda than the z ones. So we would call this an easy plane anti-ferromagnet because it wants the anti-ferromagnetism to lie in the xy plane rather than the z direction whenever lambda is positive. And by keeping this lambda in the phase diagram, it serves 2 purposes. One, it's going to help us explore and give a reason for why the superconductivity comes from superconductivity. Also, when we do apply it to twisted bilayer graphene, it turns out that that term is there, so we want to make sure this approach was robust to it. So here's the phase diagram we find. First, I'll just show it schematically. You sit at filling 2 of the Landau level, which is the quantum Hall insulators we discussed, and then you dope it a little bit. And the claim is that the phase diagram takes the following form. Whenever J, the overall average strength of the anti-ferromagnetism, is stronger than lambda, it turns out that the ground state of this model is a superconductor, even though you have long-range Coulomb repulsion. And then there's going to be a first-order phase transition when you reduce J, where it instead forms something like a charge density wave, or in general, just some state that's not a superconductor. And interestingly, in the limit where lambda does go to 0, so you have this full spin rotational symmetry, the critical J required to become a superconductor actually goes to 0. So what's the numerical evidence for this? Well, I need some way I want to argue that there's superconductivity, so we need to find an order parameter for the superconductor. And then I also want to find an order parameter for what the insulator is, the quantum Hall insulator at nu equals 2. So that quantum Hall insulator is this anti-ferromagnetism. And what we basically find is if you measure order parameters for superconductivity and XY anti-ferromagnetism, I'll get into this, indeed in the J lambda plane, the numerical result, you see this first order phase transition where all of a sudden the superconductivity turns on above this phase boundary here. And then below that phase boundary, you have a coexistence of the anti-ferromagnetism along with a charge density wave. So first, let's unpack how you look for superconductivity. And I want to be a bit pedagogical about this because superconductivity, when you look for it in DMRG, whether it's in the Hubbard model or this model here, it's quite subtle to find evidence for superconductivity in DMRG. And the reason for this has to do with the transition of going from 2 dimensions to 1 dimensions. So what would you do naively? Well, naively, if you want to show it something's a superconductor, you first identify the order parameter for the superconductor, the so-called pair correlation function. The superconducting pairs, which are condensing, come from making 2 electrons at once. So it's like a side egger thing. And the relevant superconductor here has the following symmetry. You put 2 electrons into the same point in space, so that in that sense it's like S-wave. They sit right on top of each other. But 1 electron in the Cooper pair is going to go in the top layer, and 1 electron in the Cooper pair is going to go on the bottom layer, and then they have opposite spin. So it's a little bit like S-wave, but the 2 electrons in the pair are on opposite layers. So this is the sort of superconductivity we find. Naively, you'd think, oh, in the numerics, I just find the ground state and then measure the expectation value for the order parameter. But the problem is that would work if we could do the numerics in 2D. But in 1D, we've reduced the problem from 2D onto a cylinder. So formally, the problem is actually one-dimensional, or 1 space and 1 time, not 2-dimensional. And we know that the Merman-Wagner theorem says that you can't actually break a continuous symmetry when you're in 1 dimension. Instead, what you need to check for whenever you look for superconductivity in 1D is you measure the 2-point function of the superconducting order parameter at 2 faraway parts on the cylinder, and you check for them to decay algebraically. So this is algebraic superconductivity. It's the analog of 2D superconductivity in 1D. If it wasn't a superconductor at all, you would just see it decay exponentially. So what you actually need to check for in numerical experiments like this is you need to prove that there's algebraic decay of correlations. So here's just a picture of the numerical result. You measure this 2-point function as a function of the distance along the cylinder, and then you plot it on a log-log plot. And now there's a slight caveat here, which is whenever you do IDMRG, you don't have infinite accuracy. The longer you run the simulation, the more accurate you can make it. So what I'm going to show here is what the correlation function does is you make the DMRG more and more accurate by increasing its so-called bond dimension. It's a typical parameter that's quoted. And as you make it more accurate, you see that at short distances, you always see the algebraic decay. To see the algebraic decay, i.e. this fit on a log-log plot to a line at the very largest length scales, you need to go to very, very accurate IDMRG. But indeed, you see that as you keep increasing the accuracy, it starts collapsing to this perfect power law. And interestingly, there's actually a technique you can do called scaling collapse, which lets you, prove that it does actually extrapolate to a power law, which is something we were able to do here. Okay, so there seems to be algebraic decay of the superconductivity at a fixed circumference of the cylinder. But something you might worry about is maybe this is an artifact of taking the 2D model and reducing it to 1D. So how numerically would you prove that 1D superconductivity extrapolates to 2D superconductivity? Here's another useful trick you can do. If you have a 2D superconductor, you can do finite size scaling to predict what would that 2D superconductor look like if you were to place it on a cylinder of finite circumference L. And what you find is that the exponent for the power law eta that we've been discussing that describes the fall off in 1D, that exponent needs to end up falling as a factor of 1 over the circumference. So the larger the circumference gets, the exponent gets really small and the fall off gets really slow, which gives a quantitative way that 1D algebraic superconductivity extrapolates to 2D true long-range order. So numerically, if you want to prove that your model is really a superconductor in the 2D limit, not just an artifact of the thin cylinder, what you'd want to do is scale the circumference and at each circumference measure this power law. We're actually able to do this. The plot on the left here shows the superconducting 2-point function for 2 different circumferences, say 8 to 11. You plot them both on a log-log plot. The slopes give you the power law. And by doing this quantitatively as a function of circumference, you find that they actually all collapse according to this 1 over L scaling. So this gives evidence that there's true off-diagonal long-range order in 2D. This is quite challenging to do for a little bit of history. In the Hubbard model, just square lattice Hubbard model, when you dope it, that describes the cuprates, you might ask, in DMRG, can you see superconductivity in the Hubbard model? That's only been able to see in the last year or two, and they can actually only find the superconductivity at one particular circumference. They see this algebraic decay. But at least as of yet, you're not able to take the Hubbard model, increase the circumference, and see this decreasing power law. So that's something that yet to be done. So it's cool that in this lambda level realization, the numerics are, I guess, a little bit easier or more favorable in some way, and you can actually prove it's robust in the 2D limit. So what's the evidence for the superconductivity? Or sorry, the charge density wave. Well, in order for charge density wave is pretty easy. You could just measure the local density. There's a slightly more sophisticated way to go about it, which is I'm going to measure the 2-point function for the density at one point in space and the density at another point in space. So these are these 2 plots shown here, one in the charge density wave phase at low J, one in the superconductor at high J. The origin is where the first insertion of the density is, and then this is just real space. So Y goes around the cylinder, X goes along the cylinder. You can see in the charge density wave, you have this stripy pattern. You can see these red lines here and blue lines. That's basically saying once you know there's one electron at the origin, it becomes more likely for electrons to exist wherever it's blue. That's exactly the indication of the long-range order of a crystal or a charge density wave. On the other hand, if you measure this pair correlation function in the superconductor, you actually find this attractive hole at the origin, suggesting that where one electron is, you're more likely to find a second electron. And then far away, it just melts. So it's like a liquid. There's no charge density wave order. Okay. So you can see in real space here the difference between charge density wave and superconductor. Okay, so numerically, we've shown that this model is a superconductor. But why does it superconduct? There's no phonons in this problem. So it must be some form of electron-mediated superconductivity. Where does it come from and how does it relate to the topology of the Landau levels? So that's what I want to discuss in the final part of the lecture. What's the glue here? And it turns out that the glue comes from spin textures called Skermions. So Skermions are a really beautiful part of the history of quantum Hall physics, going back to great work from Princeton by Shivaji Sandhi. I guess that was probably before he was at Princeton, his graduate work. So I first want to give a little bit of the history of what these Skermions are, how they observed in quantum Hall experiments back in the 90s, and how in the model I've just talked about, this twist model, they lead to superconductivity. So what are Skermions and quantum Hall ferromagnets? Let's for the moment forget the bilayer and just go back to gallium arsenide, where you only have a single layer. So when you look at the Landau level spectrum, you have spin but not layer, so it's like only one copy of what we were looking at before. And it's interesting to ask, how big is the Zeeman energy that splits the up and the down Landau levels? So when you look at the G factor of gallium arsenide, it's actually quite small. And so if you measure the Zeeman energy, it's something like 1/10 of a Kelvin per Tesla. So at typical magnetic fields that you do an experiment at, the cyclotron gap between 0 and 1 is like 50 times larger than the Zeeman splitting between the up and the down Landau levels. Okay, so if we forget about interactions, you then expect that your lambda level spectra would have a much, or your integer quantum Hall system would have really, really small gaps whenever you're at a filling where you're trying to split the up and the down electrons. Like if you fill only one lambda level, of course, yes, the Zeeman will slightly prefer it to be the down, but that's only like a 0.2 Kelvin distance between the up. So you'd expect the gaps to be really small, not the cyclotron gap. But that's not really what's seen in experiment. So you can do integer quantum Hall experiments at temperatures well above 0.2 Kelvin, and you'll see that at large magnetic fields, you see a very strong, so this is the integer quantum Hall here, you see a very strong nu equals 1 state, nu equals 3 state. These are odd integers, so naively they require splitting the spin, but you see they have very robust gaps, much bigger than 0.2 Kelvin. At the smaller magnetic fields, eventually reverts to only seeing the even splittings, which is more what you would expect based on the Zeeman energy. Okay, so this is a little bit of a mystery. Why do you see strong odd integer quantum Hall effects at high B fields, even though the Zeeman splitting is really small? And that's because I believe Shivaji's quips is odd integers are fractions too. You're filling half of the spin degenerate lambda level, and it's actually very important to include interactions in this problem to understand the physics of the nu equals 1 integer quantum Hall effect. So what happens here is that at odd integers, interactions cause spontaneous symmetry breaking, which cause it to just polarize in the spin space. And so nu equals 1, even if you didn't have a Zeeman effect, would actually be a ferromagnet where you polarize, say, along the Z direction. It will be slightly pinned by the magnetic field, but it's really interaction-driven effect. Okay, so nu equals 1, an odd integer, when you half fill the spin full lambda level, it spin polarizes. It's then natural to ask what textures or possible defects there might there be in the order parameter. So one sort of thing you can, of course, make is spin waves. But there's another interesting defect you can make in a magnetic system in 2 dimensions, and that's a so-called Skermion. So what I'm plotting here is the spin density in 2 dimensions. And you can imagine that predominantly it, say, points in the down direction. You can consider this interesting topological texture called a Skermion, where the spin smoothly at the core of the Skermion, shown here, the spin is up. And then radially, as you move outwards, it flops around back to the down direction. So Skermions, this winding from the north to the south pole, this is called a topological texture. It's categorized by a particular topological invariant, which is pi2 of the sphere. So it gives you a rigorous way to count how many Skermions there are. The number is quantized. The density of Skermions is measured by something called this topological density. So if you let n be your order parameter at each point in space, you can form this particular combination here. It's a spin rotationally symmetric combination. You look at the rate at which the spin texture is changing. So that's novel xn or novel yn. And then you form the triple product, the determinant between the rate that the spin is changing and the rate at which it's spinning. This gives a particular scalar number. And what's worked out in this beautiful physics of the 90s is that if you're in a lambda level and you have this topological density, as it's called, it turns out that that twisting of the order parameter actually induces a physical electron density in the problem. So the charge density ends up being exactly in proportion to the so-called topological density, where the constant of proportionality is the Chern number of the lambda level, which would be 1 or -1, corresponding to where the magnetic field is positive or negative. Now, if you integrate this expression for the charge density over the texture of one Skermion, you actually find that you get a quantized result, which says that the charge, the physical electron charge, is exactly equal to the Chern number times the number of Skermions. Okay, so the takeaway here is that in the integer quantum Hall effect, it turns out that the lowest energy charged excitations of the integer quantum Hall ferromagnet are actually these spin Skermions. This sounds extremely exotic, saying that the charge carriers are Skermions, But there's beautiful experiments from the 90s which actually show that this is the case. So one of the famous experiments is this Nmr experiment from Barrett, where what they do is they use NMR to measure the degree of spin polarization in the system as a function of the filling of the Landau level. So what they find is when they're at nu equals 1, they see a maximal amount of spin polarization. That corresponds to the fact that you have this interaction-driven quantum Hall ferromagnetism. And then as you remove electrons, you're changing nu. They see the degree of spin polarization fall off. Now, if all you were doing was removing electrons, you would expect that each electron you remove would remove 1 Bohr magneton, or G times 1 Bohr magneton, worth of spin polarization. So that would predict a particular slope for spin polarization versus the filling. That's not what they see. They actually see the spin polarization decrease extremely rapidly as a function of the doping away from nu equals 1. And if you correlate that with how many spins are getting removed every time you remove an electron, it's a large number, maybe 10 or so. So how do you explain that in terms of Skermions? Well, you can see a Skermion, by definition, flips a large number of spins, because everywhere in the core of the Skermion, the spin texture is going in the opposite direction. So if you have these big Skermions, whenever you make them, it depolarizes it. So what's happening here is every time you remove an electron, or not an electron, every time you remove a charge, it's actually going in the form of Skermions, which rapidly depolarizes it, which explains this observation in NMR. So this is a well-established experimental observation. Okay, so how do Skermions show up in our bilayer problem with a twist? So just to refresh you, we have 2 quantum Hall bilayers, or quantum Hall bilayer with equal and opposite magnetic field with anti-ferromagnetism. Well, first let's figure out what the insulating state is when you half fill it. So we have 4 Landau levels and we need to fill 2 of 4 of them. Well, as we discussed, the anti-ferromagnetism does the obvious thing. In one layer, you'll point in, say, the x direction in the spin space, and the other layer, you'll point in the negative x direction, so equal and opposite like this, due to this anti-ferromagnetic exchange. And we'll prefer to do it in the xy plane rather than the z plane because of the lambda term, if you put it there. Okay, is this a quantum Hall state? Not exactly, because in this twist on the model, one layer is positive magnetic field and the other layer is negative magnetic field. So if you compute the total Hall conductance of this, you'll be doing 1 minus 1 from the other. So there's no net Hall conductance, even though individually it looks like integer quantum Hall states. Okay, so this is the underlying order. Where does Skermions come about? Oh, sorry. Yeah, so you can show in the numerics from the DMRG that indeed the ground state of this problem, when you don't dope it at nu equals 2, is this XY order by measuring the 2-point functions. Okay, so here's the interesting physics. Let's start with this nu equals 2 anti-ferromagnet and ask what are the charged excitations when you dope it. So one thing you might do is, well, if you focus on one layer, it just looks like nu equals 1 integer quantum Hall. You just have a spin polarized Landau level. So a natural thing you could do is make a defect in the spin polarization of the top layer by making a Skermion. And by the same reasoning that applied in that situation, that Skermion would carry charge E. But there's a reason this isn't a very good thing to do in our doubled problem. We said that the 2 layers are coupled together via this anti-ferromagnetism. And wherever you make the Skermion, you need to reverse the orientation of the spins at the core. So what that means is the location, wherever you have the Skermion, this anti-ferromagnetic coupling between the 2 layers is unhappy in the vicinity of the Skermion. So you're going to pay a cost of J, where J is this anti-ferromagnetism. Okay, so it's a possible excitation, but J makes it not so favorable. Is there something better we can do? Well, at least if I ignore the electron repulsion, the obvious thing you could do is let's make a Skermion in the top layer and an anti-Skermion in the bottom layer. So what is an anti-Skermion? All you do is you take the particular spin configuration of a Skermion, and then you just apply inversion to it. So you map the north pole to the south pole. You take n to negative n. That causes everything to wind in the opposite direction, and we call that an anti-Skermion. It's a little bit like how you can have vortices and anti-vortices in the XY model. So if you put a Skermion in the top layer and an anti-Skermion in the bottom layer, clearly their spins are always anti-aligned, so J is perfectly happy. Now the question is, what's the charge of this object? So the rule for quantum Hall Skermions is that if you count the number of Skermions, that's Q topological, and then multiply by the Chern number of the lambda level, that gives you the physical electron charge. So in the top layer, it's a positive magnetic field, so it's Chern 1. So that means when you make the Skermion, it carries charge 1. In the bottom layer, it's an anti-Skermion, but also the magnetic field was flipped the other way. So it's a Chern -1 band, and two wrongs make a right. So you also get a physical charge of +1 in the bottom layer. So this composite of a Skermion and anti-Skermion in layers with opposite Chern number is actually a charge 2 excitation rather than a neutral one. And you can work out its statistics. It's just a conventional boson. Okay, so we call this a charge 2 Skermion. And the interesting question is, might this charge 2 Skermion actually be the cheapest way to put charge into the system? If it was, it meant when you dope the insulator, the charges go in as these bound charge 2e Skermions, and they're bosons. So if they can move around, then they're going to boson condense, and that leads to a superconductor. And that's what we think is actually happening. Okay, but it's not so obvious that this is actually going to be the lowest energy excitation, because there's a competition here. We said that the Skermion wants to be next to an anti-Skermion because of this anti-ferromagnetic coupling J, because that ensures that the spins are unaligned. But both things carry charge E in the two layers, and the Coulomb repulsion does the obvious thing. It does not want them to sit on top of each other. It wants these two Skermions to fly apart to avoid the Coulomb repulsion. So the question is, which wins? And the way you would look at this quantitatively is to look at the so-called pair binding energy. This is relevant to any superconductor. What you could do is compare two possible energies. One is you make two electrons and you move them really far apart and you measure their energy. So I'll call that 2e, 1e, just twice the energy of a single electron. The other thing you could do is allow for the two charges to be on top of each other, and I'll call that the energy for 2e. And if you find that it costs energy to drag them apart, that implies that there's this pair binding energy. It's like just like a hydrogen atom. It gives the binding energy for the two positive charges to sit on top of each other. Okay, so Coulomb repulsion doesn't want pair binding energy, and the anti-ferromagnetism does. Let me see where I am on time. Okay, so we can actually compute this pair binding energy two different ways. One is with extending the famous work by Shivaji and collaborators on quantum Hall ferromagnetism at u=1. You can do a nonlinear sigma model analysis and get some estimates for this energy competition. Or we can just be gung-ho and just throw the problem into DMRG and get the full quantum numerical energies for the excited states in the problem and actually just measure this pair binding energy. So let me give you the intuition in terms of the nonlinear sigma model, because it's interesting physics to know. So the way you want to describe this problem is in terms of the order parameters for the spin density in the two layers. So gamma layer is the layer, and the order parameter, I just have a unit vector in each layer describing the spin polarization. There's going to be one term in the nonlinear sigma model which says that it's a ferromagnet, so it doesn't want the spin polarization to change as a function of position. This is the usual stiffness here, the gradient term. There's another term which is quite interesting, which it says that, when you have this weird twisting, the Skirmion-like density in the order parameter, that actually induces a physical electron charge through this relation here. And that physical electron charge is going to interact through the long-range Coulomb repulsion. So this is a kind of complicated term in the nonlinear sigma model. It involves density, and each density is 3 copies of n. So it's like, in terms of nonlinear sigma model, it's like an n, a 6n term. But nevertheless, you keep it. And then finally, we have the anti-ferromagnetism, which says that the order parameters want to anti-align between the two layers. And the physics for what happens in terms of the competition is the following. If you make a really large Skermion, then its charge spreads out over a distance r. like if the radius of the Skermion is r, and that actually reduces the Coulomb energy because you're spreading out the charge in the system without actually costing any elastic penalty, because in 2D, the first term, the elastic term, is scale invariant. So if you double the size of a Skermion, it doesn't actually change the elastic cost. Okay, so the Coulomb energy wants to make really big Skermions. But if you make really big Skermions, then the repulsion in the electron density between the two layers is falling off as 1/r, where r is the size of the Skermions. On the other hand, when you look at the anti-ferromagnetic attraction, if the Skermions have size r, then this J term is acting over a size of r, because that's the region in which your spins are different, so you want them to sit on top of each other, and that scales as JR squared. So the top one is bad, the J is good. But clearly, if r becomes big, eventually this attractive always wins out over the repulsive. And that's the really interesting physics of this Skermion pairing. It gives a way to overcome Coulomb repulsion by making these big Skermions, which spread out in space, and avoiding the Coulomb. I'll kind of skip this, but you can just numerically solve the nonlinear sigma model as a function of the magnetic anisotropy J and lambda, and just measure this pair binding energy. And you indeed find that in this wedge-shaped region, which is red here, the lowest energy charged excitations are indeed Skermions. If you do it quantum mechanically, numerically, by just putting it in DMRG and solving for the ground state, you actually get a remarkably similar phase diagram. The axes are slightly different here. In the DMRG, we only did positive lambda. But the basic effect is you see that there's a pair binding energy. Things come in as charge 2s everywhere in the red region. And both of them agree, both the nonlinear sigma model and DMRG, that there's this fan-like region emanating from J lambda equals 0, where these Skermions bind into charge 2e objects. So that's pretty cool that we can numerically see the charge binding. Now, another thing you need for superconductivity is not just that pairs bind, they need to be able to move around, right? Because what drives condensation of bosons, and therefore superconductivity, is ultimately the kinetic energy of the bosons, right? You want to put them all into the ground state. So the second thing you need to show why there'd be superconductivity is to calculate the mass of these charge 2 bosons and show that they disperse so that it would want to form a condensate at the lowest momentous state. And there's very cool physics here, which is actually extremely similar. I first learned about it from the physics of Jim Eisenstein's experiments he talked about of exoton condensation. And it's the following effect. So if you take two chargey objects, which are in opposite magnetic fields, and imagine boosting them, let's have them move along at some particular velocity. Well, okay, it's a charged object in a magnetic field, so it feels a Lorentz force. Now, the interesting thing here is because the two layers have opposite magnetic fields, the charge in one layer is going to get pushed, say, to the left, and the charge in the other magnetic field is going to get pushed to the right. So when you make this 2e object move, it pulls apart the two charges. But we said that there's a binding energy which wants to bring them together. Okay, so as you pull them apart, there's going to be a cost coming from the J term. So this gives a link between the fact that increasing the velocity increases the energy of the object, even though the original bands themselves were perfectly flat. So to summarize, because of the Landau level topology, the Chern number, and the Lorentz forces, starting from perfectly flat bands, this charge T boson nevertheless actually has a non-trivial dispersion relation. And we can see this in DMRG if you just measure the energy of the charge 2 object as a function of the momentum quantum number. Very roughly, it falls onto a parabola. And that's the dispersion. And the mass of this dispersion agrees with estimates one can make from the semi-classical picture. You can see this quantitatively, this fact that they get ripped apart in the following way. You find the charge 2 eigenstate from DMRG as a function of momentum, and then you can just plot what does the density in real space look like. So I'm going to plot this on the left here, the bottom left. So the x-axis here is the distance along the cylinder. And then we plot what is the charge density of the excited state. And then the y-axis here is just looking at different excited states where you change the momenta of the charge 2e object. When you start out at low momentum, which is the bottom of the parabola, you see the integrated charge density is 2, and it just forms one lump, corresponding to the fact that the two Skermions are on top of each other. And then as you begin boosting it, making it go to larger and larger momentum, you see this charge distribution rip apart and separate into two peaks, which is the fact that the Lorentz force is pulling the 2e objects apart. And that explains the dispersion. Okay, so with that, we've kind of explained why there would be superconductivity in this model. You can see that electrons seem to go in as charged 2 pairs. There's a pair binding energy due to the Skyrmion mechanism. And then those Skermions are dispersive. So you put together pairing and dispersion that should lead to Bose condensation, which explains why this model is a superconductor, even though it's purely electronic and has long-range Coulomb propulsion. Now, the final thing I want to say, just to bring this back to the history of the quantum Hall bilayers, the spinful quantum Hall bilayers, is that in fact they're related. So here's how you can see the relation between what I've been talking about and the phase diagram I opened with. So I've been talking about superconductivity in this twisted bilayer where one layer is churn 1 and the other layer is churn -1. But suppose I apply a particle-hole transformation to exchange electrons and holes, but only in the bottom layer. So particle hole does two things. It exchanges electrons and holes, but it also effectively flips the magnetic field. So if you apply this particle hole transformation, we map the opposite B model into a same B model, okay, which is just a conventional quantum Hall bilayer. Now, how do the order parameters we've been looking at map under this? Well, in the twisted model, we had superconductivity. But if I apply the particle hole only to one layer, because these the Cooper pairs are formed between opposite layers, the superconducting order parameter turns into actually an exciton order parameter. So this actually gives a map between the exciton condensate that Jim and others were talking about and the superconductor that I'm talking about. They're actually just related by a particle hole on the bottom layer. Now, the energetics are slightly different because the particle hole does one other thing. It makes a repulsive interaction between the two layers turn into an attractive interaction between the two layers. So the Hamiltonians are not quite identical because of that. But the Skyrmion mechanism says that Skermions still can drive this exciton condensate regardless of whether the interaction between the two layers is actually positive or negative. So if one wanted to test what I'm talking about in an experiment, maybe that would give another way to do it besides realizing it in the churn band physics. Okay, last slide, I should be about out of time, is very roughly how does this physics occur in magic angle graphene potentially? So, you know, magic angle graphene, it's also observed that there's insulators, and when you dope those insulators, there's superconductivity. There's some complications there. The basic physics comes from the fact that if you look at the flat bands, there's a spin and valley degree of freedom in addition to an orbital degree of freedom. So there's 8 bands. But it turns out that there's a convenient way to look at this problem where rather than working in the basis which diagonalizes the single particle interaction, you instead work in a basis in which the graphene sublattice A or B is diagonal. So it's not the energy eigenbasis, but you could still analyze the problem in the basis which diagonalizes A and B. And if you do this, you find this very interesting effect. The 4 flat bands for each spin can now be labeled by what valley they're in and what sublattice they're in. And if you compute the churn numbers, you find that if you're in valley K sublattice A or K prime in B, it's a churn 1 band. And the other 2 bands are a churn -1 band. So if you want to map the physics of twisted bilayer graphene to my discussion today, the layers are exactly these particular combinations of valley and sublattice. And what I was calling layer is really churn sector, and what I was calling spin earlier is actually the valley. And when you do that, it maps the problem of twisted bilayer graphene onto the toy model I've been discussing. When you put back in the dispersion, that actually leads to the super exchange coupling I was talking about. This was worked out by Eslon. Okay, so that was very rapid, but I think it's a very interesting story that this twist on quantum Hall bilayers might actually be the physics of twisted bilayer graphene. Of course, that leaves open how we're going to show that this might be the case in experiments, which is definitely a subject of ongoing work. Okay, and with that, I will conclude and thank Shubayu and Mateo for all their efforts on this.
Thank you. A wonderful talk. So we got a few questions come in, so I will just read them. The first question is there a reason DMRG doesn't work for lambda smaller than 0 in slide compared to NLSM?
Yeah, it does actually work. Like I only showed it here. You can do the negative as well. It wasn't as interesting because the superconductivity ends up dying really, really quickly because the slope of the pair binding energy gets bad really quickly. But it does actually work there. I'm just not showing it here.
Okay. And can you comment on the effect of intra-layer interaction between the Skermions?
Yes, so that would show up here. So in terms of the nonlinear sigma model, you can look at the charge density in both layers. And as you're alluding to, the intra-layer repulsion and interlayer repulsion, are of the same order. So both of them are there. So it's the intra-layer repulsion that forces these Skermions individually to be big. Because let's just focus on one layer. The whole reason in quantum Hall, while you get these Skermions, is you put the charge in. If you go in as an electron, your charge is localized over 1 coulomb, like the LB scale. Sorry. So if you just put it in as an electron rather than a Skermion, you get this charge bump, which is like distributed over LB. So the typical energy to put in a local electron is going to be E squared over LB. But if you instead go in as a Skermion, due to the intralayer repulsion, it would prefer to spread that charge out over a large area. And that reduces the energy of the Skermion relative to a local electron by a factor of 2 or so. So it's exactly the intralayer repulsion which drives the charge to go in as Skermions in the first place. And then what I've described is a mechanism for the spreading out of the charge via Skermions to avoid the interlayer repulsion, and that allows them to bind into a 2e pair.
Thank you. The other question is there a reason? Oh, sorry, this one has been done. Oh, all right. Can particle Hall conjugate be mapped onto a finite grid like cellular automata?
I know it's cellular automata. I mean, do you mean a lattice model in general? Like, could you do this in a lattice model rather than continuum quantum Hall? Yeah. At least as phrased, I'll say I don't know, but I'd be happy to discuss it afterwards if it's a little more clear what the CA is.
Another question: why do we expect the two methods agree each other? Is that true? DMRG only search for highly entangled solution in this case?
So I'm going to assume that the two methods are this classical estimate we can do it analytically using the semi-classical nonlinear sigma model, and the other is this fully quantum treatment of doing DMRG. So if we mean why do these two agree with each other? Well, we only expect them to actually agree with each other when h bar is small, because it's semi-classical. And in fact, you can see that quantitatively, the shape of this boundary is a bit different. Like the pair binding is a little bit more favorable. There's more region which is red at the nonlinear sigma model. You can actually go beyond the nonlinear sigma model by going to next order in the semi-classical analysis by integrating fluctuations about the classical saddle point. And it turns out that at that next order in h bar, this computation here begins looking more like the fully quantum treatment, which is DMRG. Now, that you might also be alluding to the fact that DMRG is a low entanglement method. That's not actually so bad for finding a single that makes it very hard to find like a gas or soup of excitations above the ground state. That would have a volume law. But here all you're doing in the DMRG is putting in one 2e pair, and that adds at most about log 2 to the entanglement, so it makes it a bit more difficult but not impossible to still get accurate DMRG energetics.
Okay, thank you.
Mm-hmm.
And the other question, in which sense is the magic angle important here for the mechanism of superconductivity?
Yeah, so in the quantum Hall scenario, where I was just thinking of it as an external magnetic field, of course I get perfectly flat Landau level spectra just by the nature of, let me go back to, in quantum Hall effect, you assume there's no dispersion except for the cyclotron gap, but within a Landau level, it's perfectly flat. So that's what allows interactions to dominate over just dispersion, which would lead to conventional Fermi surfaces rather than quantum Hall ferromagnetism or fractional quantum Hall, et cetera. So the role of the magic angle is to make the single particle spectra flat so that they're flat Chern bands rather than very dispersive Chern bands. So in general, as you go far from the magic angle, you have competition between the dispersion relation and the various orders I've talked about. So that's why the magic angle is important.
Okay, thank you. How is the Methanol effect understood in Skirmion superconductivity?
Yeah, so the interesting thing is that even though the Skermions sound very exotic, they sound very exotic, but actually as a phase of matter, rather than as like an energetic mechanism, as a phase of matter, the superconductor is actually the same phase of matter as a BCS superconductor. So the Skermions are charged 2 bosons and they condense. That's not any different than in BCS. You have charged 2 Cooper pairs which condense. So as long as you have condensation of a charged object, you will expect that there's going to be the Higgs mechanism, which leads to the Meissner effect. So it doesn't matter too much that the charge, as far as that's concerned, it doesn't matter too much that the charged 2 object has this interesting internal structure of it actually being a Skermion. Meissner effect just follows from condensation itself.
Okay, thank you. The other question, what is the experimental signature of Skirmion superconductivity?
Yes, that is a very good question. So there's 2 things. One would be that there's certain very quantitative predictions for instance, like how TC might scale with density from it being in a kind of BEC limit. But those aren't particularly, it's not like you would literally see that there's Skermions. One interesting direction one can think about is if you have the superconductor and you put on a little bit of magnetic field, it will pin superconducting vortices. And it turns out that somewhat generically, if you look at the cores of the superconducting vortices in this particular superconductor, it will actually have some degenerate 0 mode, which you might be able to detect in something like STM if you could image the core of the Skermions, or like sorry, not the core of the Skermions, the core of the vortices. So why that is won't exactly be clear from what I've discussed today, but there's potentially some signatures like that. But honestly, it's a very good question. It's something we've been stuck on of what are simple experiments one could do.
Okay, thank you. We actually have a few questions from the when people register the summer school. So one question, which is also very interesting, is that what is the symmetry of the predicted Skyrmionic superconductivity in twisted bilayer graphene?
Yeah, so I didn't really have time to map, like in the quantum Hall bilayer problem, I talked about layer and spin. So the way that gets mapped into the twisted bilayer graphene is actually sublattice and valley. So what I talked about is spin is really valley. So that's kind of relevant to asking your question. Here's what in the quantum Hall language, here's what the superconducting order looks like. It's interlayer and then opposite valley. So what that maps on in the twisted bilayer language is it's like a valley singlet. Maybe the important thing to note, see, it's a little bit complicated when you talk about S versus P versus D wave. This order parameter, you can see the two electrons are directly on top of each other in real space, right? So it's not P or D or F wave in that sense. But the thing is, because these components in this problem actually map onto like sublattice in different ways, if you zoom into the graphene scale, there's some structure there which can carry angular momentum. So that was probably a confusing answer, but I would just say that the Cooper pairs overlap in real space, but there's a particular structure at the lattice scale of the Cooper pair that carries angular momentum.
Another question from the registration is there a natural relation to the charged Skermions and topological boundary mode along magnetic domain walls?
Yeah, so this is, well, like Ali Yazdani's group has interesting experiments on this sort of thing. If one has in a conventional integer quantum Hall ferromagnet nu equals 1, you could have a magnetic domain wall between a region of upspin and a region of downspin. Let me go back to a picture of a Skermion. If you zoom in on a very small piece of the Skermion here, like on the boundary, locally it just looks like a domain wall between up and something down, right? So if you make the radius of the Skermion really large and kind of make the edge flat, it will look like a domain wall between up and down. And then there's actually an interpretation of that domain wall is carrying certain modes can actually be mapped onto the fact that Skermions carry charge. Yeah, there's a precise way to see that correspondence in from a field theory point of view.
Yeah, we're still looking for that. The other question that just came in is how large is the anisotropy lambda and J in twisted bilayer graphene?
Yeah, good question. So it depends. Yeah, so in terms of this phase diagram, let me see if I can remember the number. Let me go back to the phase diagram. Sorry. So, okay, so one needs to be careful a bit that, you know, they're different models. So it's capturing phenomenologically the same physics, but we think that the lambda, so it depends on details like twist angle and the degree of lattice relaxation. But I seem to remember you tend to be in a ratio where lambda is like 0.5 and the J is also maybe like somewhere around here, also like 0.5. I mean, the thing is that I don't think it's worth getting into like, that's a very crude mapping because it's just like comparing two different models. I can say that it's not a factor of 10 too big or a factor of 10 too small. It's just like somewhere near where this phase boundary would be. So I guess that's good, but not clear that it's in one regime or the other.
Okay, I guess that's all the questions we have for today. So let's just thank Professor Zaletel again. And thank you for your wonderful talk.